Once upon a time, there were two sets of friends who went to a pool party. Neither set of friends were really dating per se. They were more along the lines of just acquaintances. In fact, when they got to the pool party, right away they began the process of mixing and mingling. But it was then that things began to change, and change dramatically. Two star-crossed lovers struck by Cupid's arrow. In fact, the attraction between the two was so powerful that they became inseparable, and they lived happily ever after. The end.
You might recall that we've talked previously about aqueous solutions. That's a solution in which water is the solvent. And recall also that solutes are those things that are dissolved into the solvent. Many ionic compounds dissolve in water, and when they do, they undergo something that we call dissociation. For example, if we put sodium chloride into water, NaCl, that sodium chloride will dissociate into sodium ions and chloride ions. We mentioned previously the idea of electrolytes that allow for the flow of electrons because of this. Well, in a double replacement reaction, we have a situation in which ions are being exchanged. We'll have two aqueous solutions, solutions that contain dissociated ions, and those solutions will come together to form a product. There are three types of products that come from double replacement reactions. You can have a solid that forms, we call that a precipitate. You can have a liquid that forms, normally water, or you could have a gas that forms. In order to understand a little better about what's going on when we put these aqueous solutions of ionic compounds together, we use complete ionic equations and net ionic equations. Complete ionic equations show all the particles that exist in that solution. But as we could see from our love story, some particles are really involved in the reaction while others not so much. They don't really participate. Those ions are known as spectator ions. While a complete ionic equation will show us all those particles, including those spectator ions, a net ionic equation does not. A net ionic equation only shows us the particles that are directly involved in that reaction. So let me show you three examples of how we'll take a chemical equation of a double replacement reaction and convert it to a complete ionic equation and then a net ionic equation. Here we go. Let's start with a double replacement reaction that produces a precipitate or solid, like the reaction between lead-2 nitrate and potassium iodide. Here's the chemical equation for that reaction. Notice that it's been balanced. Now it's real important for us to remember that we must have a balanced equation to do all this. We have to obey the law of conservation of mass. You'll notice that the reactants are aqueous solutions. That is to say that their ions are going to dissociate in water. So in the complete ionic equation, we're going to show what ions are present in those two solutions. For every formula unit of lead-2 nitrate that you put into water, that formula unit will dissociate to give us a lead-2 ion and two nitrate ions. So to begin our complete ionic equation, we'll show a lead-2 ion, that is a lead ion with a +2 charge, and two nitrate ions, each with a negative charge. We'll also show those ions to be aqueous, since they are dissociated in solution. Next, let's look at our potassium iodide. For every formula unit of potassium iodide that goes into water, it dissociates to give us one potassium ion and one iodide ion. Since we have two formula units of potassium iodide in this equation, we need to show in the complete ionic equation that there are two potassium ions with a +1 charge and two iodide ions with a -1 charge. And again, these ions are aqueous. And that gives us everything we need on the left side of our complete ionic equation. Let's look at the right side. Our two possible products are potassium nitrate and lead-2 iodide. We can use a solubility table to show that lead-2 iodide is our solid. That is, it doesn't really dissociate much in water. That will be our precipitate that forms. Potassium nitrate, on the other hand, is aqueous. It dissolves in water. We see that we have 2 formula units of potassium nitrate in our equation. So, just like we did on the left side, we'll show that in our solution we have 2 potassium ions with a +1 charge and 2 nitrate ions with a -1 charge. And again, those ions are aqueous. But for the lead iodide, we'll keep it intact. After all, when it's in solution, it does not dissociate well like the others do. So we'll keep it as a solid. Lead to iodide, solid. This represents our complete ionic equation. So now how do we know what to put in our net ionic equation? It's very simple. We look at the left side of the equation and the right side, and we look for any ions that really haven't changed from the left side to the right side. Those are going to be our spectator ions. Those are the ions that don't really participate in the reaction. When we look on the left side, we see that we have 2 nitrate groups on the left side, and on the right side we have 2 nitrate groups as well. They haven't changed. Therefore, those are spectator ions. We'll cancel those out. The same can be said for the 2 potassium ions on the left side. No change from the right side, in which we see 2 potassium ions there as well. So we'll cancel those out. The potassium ions and the nitrate ions are our spectator ions. Everything else participates in the reaction. So for our net ionic equation, we'll show an aqueous lead-2 ion combining with 2 aqueous iodide ions to form lead-2 iodide solid. And that is our net ionic equation. It shows us who the real players are, lead-2 and the iodide ions. It's sort of like going to the movies, whenever we get around to going again. We don't go to the movies to see who the key grip was. Sorry, key grips. Or really the supporting actors in the movie. We go to see the stars of that movie, don't we? So the spectator ions are sort of like those supporting cast members, while the net ionic equation shows us the true stars of the show. The nitrates and the potassium in this case, supporting actors. Their purpose was to bring the 2 lovebirds together, the stars of our show. Make sense? How about another example? Let's use a double replacement reaction in this case in which water is formed. Here we have a neutralization reaction between an acid and a base. We have sulfuric acid and potassium hydroxide. Both of these reactants are aqueous solutions, and when we do the replacement reaction, we find that the hydrogen and the potassium switch partners, don't they? We have potassium that combines with the sulfate group to make K2SO4, and we have hydrogen that combines with the hydroxide groups to make water. When we balance the equation, we see that we need 2 potassium hydroxides to react with the 1 sulfuric acid to give us 1 formula unit of K2SO4 and 2 waters. Now we can confirm that K2SO4 is aqueous. Water is our product here. It is a liquid. It's not aqueous. We don't dissolve water in water, okay? Water is just a liquid. So let's form our complete ionic equation, starting with the 2 formula units of KOH. That's going to give us 2 potassium ions with a +1 charge and 2 hydroxide ions, each with a -1 charge. Those ions are aqueous. Let's move on to the sulfuric acid. That's going to give us 2 hydrogen ions with a +1 charge and a sulfate ion with a -2 charge, each of which is also aqueous. By the way, it's important to remember to write 2 hydrogen ions. Don't write H2 with a plus charge. That's incorrect. On the other side, we'll separate the K2SO4 into its appropriate ions. For each formula unit of K2SO4, we'll get 2 potassium ions with a +1 charge and 1 sulfate ion with a -2 charge. Finally, our water molecules stay intact, so we just write 2H2O. And that finishes our complete ionic equation for this reaction. To give us our net ionic equation, we simply cancel the spectator ions. So what are the spectator ions here? Right, the potassiums are the spectator ions, as well as the sulfate group. Very good. Here's a hint for you, by the way. When you look at the products, the one that's aqueous will be composed of your spectator ions. And likewise, the one that's solid, liquid, or gas is going to be involved in your net ionic equation. You see? So for our net ionic equation, we write 2 hydrogen ions with a +1 charge each, and 2 hydroxide ions with a -1 charge each, all of which being aqueous, yield for us 2 molecules of water. And that is our net ionic equation. Let's do one more for you. This one will produce a gas for us. It's the reaction between hydroiodic acid, Hi, and lithium sulfide, Li2S. Both of these are aqueous solutions, and when we're determining our products, remember that we switch partners, don't we? And remember that positives always bond with negatives. They don't bond with each other. In this case, our lithium ions will combine with the iodide ions to form lithium iodide, and the hydrogen ions will combine with the sulfide ion to form hydrogen sulfide, H2S. The lithium iodide is very much aqueous. Hydrogen sulfide is our product. It's a gas. Let's work on our complete ionic equation now, starting with the hydroiodic acid. Since we have 2 formula units in our equation, we say that we have 2 hydrogen ions with a +1 charge each and 2 iodide ions with a -1 charge each, all of which are aqueous. Next, let's dissociate our lithium sulfide. In each formula unit of lithium sulfide, we have 2 lithium ions with a +1 charge each and 1 sulfide ion with a -2 charge, all of which are aqueous as well. On our product side, we'll dissociate the lithium iodide. There are 2 formula units of lithium iodide, so that means that we have 2 ions of lithium with a +1 charge each and 2 ions of iodide with a -1 charge each, all of which are aqueous. And finally, we have the hydrogen sulfide. We leave the hydrogen sulfide together because it's our product. It's a gas. Remember, it's only the aqueous compounds that we're dissociating. So this is our complete ionic equation. Now it's time for us to cancel the spectator ions to give us our net ionic equation. So we cancel the iodide ions and we cancel the lithium ions. And that will leave us with 2 hydrogen ions with a +1 charge, aqueous, plus the sulfide ion with a -2 charge, aqueous, yields for us hydrogen sulfide gas. There you go, your net ionic equation for this reaction. So that's all we're doing for this video. In this video, we talk specifically about how to write complete ionic equations and net ionic equations based on a double replacement reaction. Hopefully these examples have been helpful to you, but if I can do anything else for you, let me know. Until next time, God bless.